Hey crew. So before we get started, we're going to start on this worksheet. We are going to do a brief reminder of everything kind of from this chapter, mostly naming right now, and then we'll just get right into it. All right, so before we get started, a few things to think of. When you get your periodic table, you're going to first draw your stair stepper like this, so to the left of boron and all the way down, and that essentially separates the metals from the nonmetals, where the portion up here is nonmetal, and the portion over here is going to be the metals. So over here is all metals. Let me see if I can pull this up a little bit. Okay, don't forget hydrogen belongs in the nonmetal over here, so hydrogen goes over there. The next thing you're going to do is you're going to take and put the charges of each thing. 1 plus, 2 plus, 3 plus, 4 plus or minus, 3 minus, 2 minus, 1 minus, 0. Now those are not the charges that they always are. Those are the charges when they're an ionic compound. An ionic compound is when you have something from over here, something from over here, and they're paired up. The other thing we're going to want to do is this. Like that, okay? These have a 3 plus charge. These two have a 2 plus charge. And this one down here is a 1 plus charge. So silver's 1 plus, zinc and cadmium are 2 plus, and aluminum, gallium, and indium are 3 plus. All right. So once we have that all kind of set, we can even look at polyatomic ions. To remind you of the polyatomic ions, we started with like carbon. To the right is that. To the right of that is nitrogen. Underneath that is phosphorus. To the right of that is sulfur. To the right of that is chlorine. Underneath that is bromine. And underneath that is iodine. Okay, so essentially I did carbon, nitrogen, phosphorus, sulfur, chlorine, bromine, iodine, just that little pattern thing. Okay, so to these we're going to add an O to all of them. Then all of these get a 3, except for the inside ones get bonus points because they're getting spooned, I think is what we said in class. Cool. Now we look at charges. There's 2 here, so this is 2 minus, 1 minus. There's 3 here, so 3 minus, 2 minus, 1 minus, 1 minus, and 1 minus, okay? You don't need to write the 1, you can just write a minus. These are equivalent. 1 minus and a minus are the same exact thing. All right, these are our 8s. If you remember, this is carbonate. I'm not going to go through all of them. And this one's like bromate, for example. Nitrate, phosphate, sulfate, chlorate, bromate, iodate. Those are our 8s. Now, once you know these, and you will probably, hopefully, write these down in the periodic or on the exam when you get it. So you go through, you do this, you do the triangle, then you write these down. You can derive a lot of stuff from that. So, for example, if nitrate is NO3 negative, nitrite is NO2 negative. 1 less oxygen, but everything else remains the same, right? Then we even talked about like hyper and hypo. So let's look at chlorate here. This only works for these 3. Only the chlorate, bromate, iodate, only those 3 can do the following. So we said, okay, chlorate is ClO negative. Chlorite we would know would have to be ClO2 negative. 1 less oxygen, everything else the same. Then we talked about hypo. If you have hypoglycemia, then you have low blood sugar. So hypochlorite, that means less than the chlorite, would be ClO negative, just a 1. 3, 2, 1. Hyper, we get rid of the hype, we just call it perchlorate. 1, 2, 3, 4. Per means more. We're going to have 4, ClO4 negative. 4, 3, 2, 1. Everything else remains the same. The charge is the same. The chlorine's the same. The oxygen's still there. Just there's 4 of them here, 3 of them there, 2 of them there, 1 of them there. You'll need to know that. Other ones we talked about, we discussed ammonium. We discussed, oh, it's hydroxide. We discussed acetate. And I'm pretty sure we did another one. Cyanide, that's what it is. Cn negative, we called it cyanide. Okay. Last but not least, so we did the eights, we did the ites, we did the perchlorate, the hypo, we did the weird ones over here. There's one more section that we need to know, and that's the hydrogens. So we didn't talk too much about it. It was on your homework and it was on your lab, but it's pretty straightforward. If I take an H plus and I add it to this carbonate right here, hopefully you agree, ClO3, 2 negative is carbonate. If I take this and add it to that, it becomes HCO3. But now you add a 2 minus and you added a positive. If you have negative $2 in your account and you add $1, you just only have negative $1 now. So negative 1 is a charge of this, and this is a really straightforward name. That's hydrogen, that's carbonate. Together, it's called hydrogen carbonate. You can do the same thing for like anything that has a 2 negative charge or above. So carbonate, phosphate, sulfate. You can do it for any of those. You can make a hydrogen sulfate or a hydrogen phosphate. For example, if I wanted you to do hydrogen phosphate, we know phosphate is PO4, 3 negative, because we memorize it as PO4, 3 negative. We know hydrogen is an H plus, so when we mix them together, we get HPO4, but now it would have a 2 negative charge on it. And that's hydrogen phosphate. All right, so that's all the polyatomic ions that I can personally think of. If there's more, let me know, and I'll add them to the notes here. Okay, so we talked about 2 different types of naming. Ionic and molecular, but ionic itself came into 2 types. So there's ionic type 1 and ionic type 2. Okay, and ionic type 1, we know the charge of the metal. Let me give you an example. If I asked you to name CaCl2, you would call this calcium chloride. You wouldn't need a Roman numeral because calcium is in the second column. We know its charge. We know the charge of everything in the first column, everything in the second column, and we know things of this chart of this triangle right here too. Okay, calcium's right here. We knew its charge. Therefore, there's no reason to write its charge in its name. So, for example, if we went backwards, let's pretend we did not know. Let's pretend we didn't know that. When we go to build this, we're like, oh, calcium, it's right here. It's in the 2 plus charge. Chloride is over here. It's in the 1 minus column. So chloride has a 1 minus charge. And then you just look at the charges. All we ever do when we put these together is look at the charges. We ignore the rest of the crap. So here's a 2 plus, here's a 1 minus. So you need 2 of those minuses to cancel those 2 plus. And CaCl2 is the only possible way to build calcium chloride. Okay. Now let's look at a different one. Let's look at molybdenum. Molybdenum 4 sulfate. Let's go crazy here. Let's say I want to build molybdenum 4 sulfate. Okay. In order to build molybdenum 4 sulfate, I'd have to look at that 4 right away. Molybdenum is here. We don't know its charge. And that's why I had to indicate it with the Roman numerals. Again, molybdenum's here. It's outside of the first column, it's not in the second column, and it's not in this triangle. Therefore, you need a Roman numeral. So I put the Roman numeral. What this is telling you is that it's got a 4 plus charge. Sulfate, we know it's the outside of the spoon. It's SO4 with a 2 negative charge. We never care about anything else. We just look at the charges. The MO's got a 4 plus. The SO4 has a 2 minus. So we got a 4 plus and a 2 minus. We need more minuses, right? We need 2 of those. If we need 2 of those, we don't take that 2 and distribute it to random places in this SO4. We don't let it freak us out. Remember, this SO4 stays together. All we care about is that charge. So the SO4 stays together and we need 2 of them. So when we go to put it together, we say MO, and that's when we use the parentheses, that we have an SO4 inside the parentheses, and we want 2 of them. So you put the 2 on the outside. This is molybdenum 4 sulfate. What if I went backwards? What if I said, great, name that sucker, name it. Well, in order to name it, the first thing you would do is recognize that molybdenum is here. It's outside of the first, second column in the triangle, therefore we'll need a Roman numeral. So naming it is relatively straightforward at first. You're like, okay, that's molybdenum sulfate. But then you should recognize that you need to have Roman numeral in there because it's molybdenum. So now your question becomes, oh, what is the charge of this thing? Well, you know it had sulfate, and it had 2 of them. So I'm going to draw 2 SO4, 2 negatives. And it had 1 molybdenum. You know that the total charge of this had to have been 4 negative, leaving only one option for the molybdenum. It had to have been 4 positive, because they have to cancel each other out. And that's how you get molybdenum 4 sulfate. So be able to go back and forth. Take a name, build the formula. Take the formula, build a name. If you can't do that, you're not going to be ready. Okay. So that's type 2 ionic compounds. Last but not least, we talked about type 3. We call these molecular compounds. Molecular, also known as covalent. So they're molecular and covalent compounds. This is when you have 2 or more nonmetals. Cool. So anytime you have 2 or more things coming from here, put together. Let me give you an example. N2O4. This would be dinitrogen tetroxide. If you need help with those prefixes, tetroxide, then go back through and look at the notes we have, where I do have notes for this. I think it's worksheet 4B has them. So di and tetra. Di means 2, tetra means 4. 2 nitrogens and 4 oxides. Make sure you're going to end it in "ide." All right, with that review, let's go ahead and get started. Let's do this worksheet. Okay, all we're going to do is name these. So the first thing I see an ammonium and I see a chloride. I know the charge of ammonium, I know the charge of chloride. This is therefore ammonium chloride. If you want to go back, just remember that this is an NH4 with a positive charge and Cl negative. Remember, this is a weird one because it's all nonmetals, right? But it is nevertheless a part of an ionic compound. It acts like a metal. Okay, now we get to this one. This is going to be iron nitrate of some sort. But when you look at iron, iron's right here. If iron's right there, it's not there, it's not there, it's not in the triangle. We need a Roman numeral. So this is going to be some kind of iron something nitrate. And we got to just go figure what that something is. We know that nitrate by itself is NO3 negative charge. We have 3 of them for a total of 3 negative. If all of our nitrate is 3 negative, what must our iron be? Well, it certainly has to be 3 positive. These amounts have to cancel each other. And that's why this is iron 3 nitrate. Then we get to Tiber. This is going to be some kind of titanium bromide. But once again, I recognize that titanium is not in the first or second column, nor is it in the triangle. Okay, titanium is right here. So I need Roman numerals. We know that I have 3 bromides. Each of them has -1 charge because they're in the 7th column. And therefore we have a total of 3 negative coming from there. Our Ti therefore must be 3 positive. So this is titanium 3 bromide. MgNO2. So NO2, I know NO3 was nitrate. NO2 therefore must be nitrite. This is some sort of magnesium nitrite. Now my question is, do I need Roman numerals? Well, magnesium is here in the 2nd column. Do we know its charge? We do. It's 2 plus. It has to be 2 plus. There's no other charge it can be, and therefore we don't need to write the charge. It's just magnesium nitride. Okay, we get to here. Be, that's beryllium. Beryllium is in the second column. We know its charge. HCO3, that's hydrogen carbonate. And so it's pretty straightforward. This is just beryllium, hydrogen carbonate. N2O5, that's 2 or more nonmetals. So there's no metal in here. This is covalent. That's when we get to use di-tritetra. There's 2 nitrogens and 5 oxygens. So this is di-nitrogen. 5 is pentoxide. Cool. Okay, moving on. AlCN3, I recognize this CN is cyanide. And aluminum is in this triangle right here. It's got a 3 plus charge. We know it's charged, therefore we don't need Roman numerals. This is just aluminum cyanide. Cool. No need to name it, or no need to do Roman numerals. Lead. Lead is right here. Okay, that's outside the triangle, and it's not in the first or second column. Therefore, we don't know the charge of lead. We're going to have to use Roman numerals. SO4 I recognize as sulfate. So this is lead, something, sulfate, and we have to figure out what that something is. We know each sulfate has a 2 minus charge, and there's 2 of them, meaning the total charge is a 4 minus from the sulfates. So the one lead must therefore be a 4 plus. And that's why this is lead 4 sulfate. Tin is also, it's right next to lead. It's outside the triangle. It's outside the first or second column. So tin will need a Roman numeral. It says sin if you don't know tin. I almost started writing sin. This is tin something. This is selenium. So as an anion, it would be called selenide. Okay, they all end in IDE. Any of these that are coming straight from the periodic table. Chloride, bromide. That's not straight from the periodic table. That's a polyatomic ion. That's why that's nitrite. That's an 8. Cyanide. You just got to memorize. But all right, so let's go look at what it is. So selenide is right here underneath sulfur. It's in this 6th column, so it's got a 2 minus charge. So selenide has a 2 minus, but there's 2 of them, for a total of 4 negative coming from the selenide, which means tin must be what? It has to be 4 positive. And that's why this is tin 4 selenide. All right, moving on. We got lead, and PO3 is phosphite. Remember PO4, do we have it up here? I guess not. PO4 is phosphate, PO3 is phosphite. This is some kind of lead phosphite, and we know we have to find the Roman numerals for lead because it's outside the triangle in first and second column. Phosphite is PO3 with a 3 negative charge. So lead must therefore be 3 positive. That's why this is lead 3 phosphite. Now we get to this one. Cu is copper. This is phosphide. So this is some sort of copper phosphide. Again, it's just an ide because it's coming from the periodic table. The P is coming from the periodic table. Copper, however, is right here. It's outside the triangle, so we have to include its charge. So phosphide is here. It has a 3 negative charge. So the total from the phosphide is 3 negative, meaning the total from all 3 of these coppers must be 3 positive. My question to you is, if they all add up to be 3 positive, what is each one? Well, each one has to be a 1 positive, and that's why this is copper 1 phosphide. If you didn't get that, watch it again. And I'm actually going to build it backwards real quick just to make sure you understand. Let's say I didn't know anything about the formula. If I know copper 1, I know that it's Cu with a +1 charge. I know phosphide from where it's at in the periodic table is a P3 negative. What do I need more of, negative or positive? Hopefully you agree you need 3 total positives, so we need to multiply that by 3. And what that gives you is Cu3P. We got the exact same thing back, so be able to go back and forth again between those. All right. Now Mn is not manganese, it's not magnesium, it's manganese. Manganese. Okay, so this is going to be some kind of manganese. And then SO3 is sulfite. Manganese is here. It's outside the first and second column and things, so and triangles, so we need to know its charge. We need each sulfite is SO3 with a 2 negative charge, and instead we got 3 of them for a total of 6 negative. So we have a total of 6 negative coming from the sulfite, and we have 2 manganese. But we know that those 2 must add up to 6 positive. So what is the charge of each manganese? Hopefully you agree each one is a 3 plus. And that's why this is manganese 3 sulfite. If you don't believe me, take manganese 3 sulfite and build it, and you'll get this thing back. Okay, chromium 6 phosphate. So chromium 6 would be a Cr6 plus. Phosphate is PO4 with a 3 minus charge. Don't look at anything other than the charges. So we got a 6 plus and we got a 3 minus. You know you need more 3 minus, so you're going to multiply this by 2 to give you a total of 6 minus now. When you go to put it over here, Cr, but you want to multiply this whole thing by 2, the P, the O, and the 4. So you put the P, the O, and the 4 inside parentheses, and the 2 on the outside. Lithium iodide. Lithium is Li plus, it's in the first column. Iodide is I negative, it's in the 7th column. And you just need 1 of each. Li is your answer. All right, lithium. Again, Li plus. Sulfite is S2 negative because it is in the 6th column here. You need 2 lithiums and 1 sulfide, and you get Li2S. Next we have vanadium sulfide. Vanadium is V with a 5 plus charge. Sulfide is S with a 2 negative charge. The only way to get those to work is to find a common factor between them, which is going to be 10. So I'm going to have to multiply that by 2, and I'm going to have to multiply that by 5 in order to get 10, if that makes sense. 2 times 5 plus gives me 10 plus. 2 times 5, 2 negative times 5 gives me 10 negative. So here we have V2, S5. All right, next we have gallium chloride. Gallium happens to fall in this triangle, so we know it. We don't need a Roman numeral. Because we already know its charge. It's Ga3 plus. Chloride is Cl negative. We need 3 of those chlorides to cancel out the gallium, and GaCl3 is my answer. Lead 2 chloride. I like Roman numerals because you don't have to look at the periodic table at all and figure things out. You just know that lead has a 2 plus charge. It makes it simple. And chloride is Cl negative. How many chlorides do you need to cancel out the lead? Well, you'll need 2. And Pb, Cl2 is your answer. Then we get to molybdenum. We have MO2 plus, and sulfate is SO4 2 negative. You just need 1 of each to cancel each other out. And MoSO is your answer. Last but not least, we have this one. It's tetraphosphorus. So some kind of phosphorus, some kind of oxygen. Tetra means 4 phosphoruses and 10 oxygens. So P4O10 is the answer I'm looking for. All right, so if you had any trouble with that, go back to the original naming lectures and see if you can figure things out, or go back and just rewind it and go through it again. Make sure you really test yourself. Don't just, like, can you pause the video, for example, and do the entire worksheet without looking? If you can, then you're in pretty good shape. If you can't, then you've got some practice to do. Okay, I'm gonna go through and do these Lewis structures here, but maybe before I do, it might be helpful to remind you of the shapes we talked about. So we kind of broke everything down in the following. We said, okay, that you have bonding groups, or actually I think we called them electron groups. Let's keep the vocabulary the same. Electron groups. And we said an electron group is a single bond, a double bond, a triple bond, or a lone pair. All four things constitute one single electron group. Then we had lone pairs. So the amount of lone pairs something has. Then we said, based on that, we could tell its electron geometry, its molecular geometry, and its bond angle. Okay. The way we did it is like this. We said you're gonna have 2, 3, 4, 4, 4. That's it. All we did was 5 of them? A 2, a 3, a 4, 4, 4. For the 2, we had 0 lone pairs. For the 3, we had 0 lone pairs. And for the 4s, we went 0, 1, 2. The electron geometry, when it has 2 electron groups and 0 lone pairs, we said it was linear. Remember, the point is to get those electron groups as far away from each other as possible. We also said anytime the lone pairs are 0, these two things are going to be the same, the electron and the molecular, so this is linear. It's got a 180-degree bond angle. For 3, 0, we said that looked like a triangle in a plane, and that's why we called it trigonal planar. Once again, we had 0 lone pairs, so this is also trigonal planar. We said its bond angle is 120 degrees. In other words, 360 divided into 3s. Then we had 4 and 0. When it was 4 and 0, 4 electron groups, we called this tetrahedral. We also called this tetrahedral because it had 0 lone pairs. The bond angle here was 109.5 degrees. When we had 1 lone pair, I think we used ammonia as the example. We said something like this, just to remind you. So it has 4 groups, 1, 2, 3, 4, but one of them is lone pairs. We called this trigonal. Oh, excuse me, I'm getting ahead of myself. The electron geometry is the same because you got 4 things. This is tetrahedral. And it will be for all 4. All 4 electron geos will be tetrahedral. But its molecular geometry, when you're looking at just the atoms, is a little different. They look like a pyramid, like a triangular pyramid, and that's why we call it trigonal pyramidal. And we know this lone pair squishes these bonds together, so we know that this was less than 109.5. The other example I gave was like water, or maybe H2S, since you'll do water later. This has 1, 2, 3, 4 bonding groups, but 2 are lone pairs. Once again, because it's 4, the electron geometry is tetrahedral, meaning the electron groups arrange in a tetrahedral pattern. 1, 2, 3, 4, as far away from each other as possible, but the molecular geometry, just looking just at those 2 things, is what we call bent. Because it has 2 lone pairs squeezing those hydrogens together, this is less than 109.5. All right, so we're going to use this once we build Lewis structures. We're going to use the electron groups and the lone pairs to figure this information out. Well, let's do it. Okay, so in building Lewis structures, remember we've always followed a pattern. We first count valence, we 2 put together you're putting the first one in the center, usually, the least electronegative one in the center. 3, add octets. And 4, count valence again. Now, unfortunately, I'm using a pen, so I can't erase things when I do the octets, so I'll see how this goes. But, again, first things first, count valence. So here we have 4. To remind you of valence in case you ever missed it, first column has 1, second column has 2, third column has 3, 4, 5, 6, 7, 8. So carbon's in the 4th column, therefore it has 4 valence electrons. We have 4 plus, whoops, I'm getting ahead of myself. 4 plus 3 times 1 from the hydrogen, plus 7 for a total of 14 valence electrons. Meaning at the end of the day, we can only have 14 electrons all over this whole structure. So the carbon goes in the center, 3 hydrogens on either side, however you want to place them is fine, and then a fluorine here. It would have been fine if your fluorine ended up over here, or even down here. I don't care. You need to have 3 hydrogens bonded and 1 fluorine bonded to the carbon. Now we add octets. So we put them together. Now you're going to add octets. It seems to be that most people miss this step. They just try to start guessing things. Don't guess. Don't get ahead of yourself. Just follow the steps because it works every time. So we're adding everything to have an octet. Carbon already has 2, 4, 6, 8. It's good. Fluorine, you just need boom, 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 boom. Don't forget, hydrogen has to be on the outside. You can only ever have 1. Now fluorine has 2, 4, 6, 8. It's good. So let's go ahead and count the electrons and see if they add up to 14. 2, 4, 6, 8, 10, 12, 14. We're good. This is the structure. Okay. Now that we know the structure, now we can worry about these other columns. We couldn't do these before we know the exact structure. Okay, so it looks to me like carbon has, looking only at the carbon, which is what you're doing for these shapes. I'm going to say that again. You're only looking at the carbon, the center atom, and you ask yourself, how many bonding groups are on it? There's 1, 2, 3, 4. It has 4 bonding groups. Does carbon have any lone pairs? It's got 0 lone pairs. So we're in a 4-0 category. 4-0. Tetrahedral, tetrahedral, 109.5. Tetrahedral, tetrahedral. Whoops, I didn't even ask that. Let's put bond angle over here, because you should do it. Bond angles are going over there, 109.5. Okay, now we can look at the polarity. Remember, polarity is anything that has an electronegative atom. Electronegative meaning something up and to the right of the periodic table like this. So it's got an atom that's over in this general area. And it's got some kind of unevenness to it. It will be polar. So this fluorine right here is the most electronegative atom possible. So it pulls the electrons this way. So it does have a dipole going that way. And this is, yes, absolutely polar. Anytime you have something that's like uneven, it's going to be polar. Okay, let's get to water. Oxygen goes in the middle, hydrogen's on either side. It looks like 2 times 1 plus 6 gives me 8 total electrons. So when I go to place the octet, 2, 4, 6, 8, I'm already good. I got 8. Okay, so now we look at groups. I have 1, 2, 3, 4 electron groups. I'm going to do that again. 1 here, 1 here, 1 here, and 1 here. 4 electron groups. Of those, I have 1, 2, which are lone pairs. So we're looking at a 4-2 situation. It's right here. With a 4-2, tetrahedral, bent, less than 109.5. So you're going tetrahedral, bent, less than 109.5. Cool. Now we look at the polarity. You have to remember what it looks like. It's bent. So even though we drew it in a line, that's not what it looks like in real life. In real life, it's bent. It looks like this. Okay. And when you do that, hopefully it's a little easier to see that this oxygen, which is far up and to the right over here, is much more electronegative than hydrogen. It can actually pull electrons toward it. So the electrons move up that way. And this is also polar. If it had been linear, this would not have been polar. In fact, that's why I do this next problem. So in this next one, we have a carbon, which is 4 plus 2 times 6 for each sulfur. Gives me a total of 16 valence electrons. I'm going to do this on a different page, just so I don't ruin it too much. Okay. So for the CS2, I'm going to put the carbon in the center, and I'm going to put a sulfur on either side. I'm going to give everything an octet. This isn't going very well. Boom, dot, 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 dot. But when I count it out, I have 20 electrons, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So what you do is you get rid of a lone pair on two adjacent, excuse me, on two adjacent atoms. So I get rid of that one, I get rid of that one, and I draw a bond between them. Now the sulfur and carbon still have octets, but we've gotten rid of an extra set of electrons. Now when you count it up, 2, 4, 6, 8, 10, 12, 14, 16, 18, we have 18. So we still need more. So I'm going to do that again because I know I just threw a random number at you without showing. 2, 4, 6, 8, 10, 12, 14, 16, 18. We still got too many because we can only have 16. So I'm going to get rid of a lone pair there, and draw a bond between them. So what we end up looking like is a carbon, double bond it to a sulfur, double bond it to another sulfur, and each sulfur has two lone pairs on it. Like that. Okay, that's our 16. All right, now we can look at bonding electron groups. Remember, electron group is any single, double, triple bond, or a lone pair. This has double bond and a double bond. It's got 1, 2 electron groups. 1, 2 electron groups around that carbon. None of which are lone pairs. There are no lone pairs in the carbon. So we're at 2, 0. Linear, linear, 180. Linear, linear, 180. Now we ask about polarity. Because it's in a line, it's a straight line. Yeah, that sulfur is pulling that way, but this sulfur is also pulling that way. They're equal and opposite, so they cancel each other out, and this is not polar. All right, in class, I believe I had you change this to HCN. That's because anytime you have just two atoms, it's always going to be linear. So if you do CN negative, it's going to be linear no matter what. But HCN makes it a little more fun. HCN, we have 1 plus 4 plus 5 for a total of 10. I'll do it over here again. So we put the C in the center with an H and an N and give everybody an octet. And then count because we know we can only have 10. 2, 4, 6, 8, 10, 12, 14. We got 14. So I cross this out, draw a double bond. Now that gives me 12. 2, 4, 6, 8, 10, 12. So I cross this out, and draw another bond. Now you got a triple bond. In other words, your final thing looks like this. It's an H bonded to a carbon with a triple bond to a nitrogen and dots. When I look to see its shape, I see it's got 1, 2 electron groups. Remember, it doesn't matter if they're single or double or triple. If they're together, they're just 1 electron group. So 1, 2 electron groups coming off that thing, 0 lone pairs. We're looking at another linear situation, 180. And then the polarity, let's find out. Do you remember cannot clean out fridge? We said, no, you cannot clean out your fridge. They said it will come in handy a lot. Nitrogen's more electronegative than carbon. So when we go here, nitrogen's pulling electrons away from carbon. It's pulling this way. We ignore the carbon hydrogen. We never pay attention to it. So what that means is this is, yes, in fact, polar, definitely polar. Bi3, there's something special about boron. Remember the exceptions? We said hydrogen makes 1 bond, beryllium makes 2, and boron likes to make 3. Okay, those are our exceptions. So when we go to put it together, we put boron in the center, and we add the 3 I's. I didn't count up electrons, but I should. It's a hint because boron only has 3 valence electrons, so when you look to find boron, you'll say, oh, it's only got 3. Plus 3 times 7 for a total of 24 valence electrons. Okay, so I put boron in the center, I added the 3. I'm not going to give boron an octet because it already has 3, but I will double check to make sure. Don't forget to give the iodines octets. They are not one of the exceptions. So when you count up, you've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. You are good. This is the Lewis structure. If I look at total groups, I have 1, 2, 3 groups. 0 of which are lone pairs. So I'm at 3, 0 situation, trigonal planar, 120. So I got trigonal planar, 120. Last but not least, is it polar? Well, you have pole there, and a pole there, because they're all equal, like opposite. Like I talked about, I have a dog toy. It's a circle. It's got 3 ropes, and when my dogs all pull on it, the rope doesn't go, the toy doesn't move at all, because it's not polar. They're all equal opposite direction poles. Okay. Last but not least, we got this CH2O. I'll draw it down here. So first things first, we got 4 plus 2 times 1 plus 6, so a total of 12 electrons. So put carbon in the center, hydrogen, hydrogen, oxygen, and then give everybody an octet. But now when we go to count, we've got 2, 4, 6, 8, 10, 12, 14. We got 14, we got 2 too many. So you get rid of 1, and draw a double bond. Okay. So your final structure ends up looking like an H to a C to an H with a double bond to an O, and that O has 2 lone pairs on it. For its electron geometry, we look at how many electron groups are on it. Just the carbon has 3, and I see 0 lone pairs. So it's a 3-0 situation, just like up here. It's trigonal planar, But now let's look at the polarity. It's not 3 of the same things now. You have O. O is way more electronegative than carbon, right? It's way closer to fluorine. So this is pretty electronegative. It's really pulling electrons that way. And this is in fact polar. It doesn't have any other opposite pole to change that. Oh, and it was 120, my bad. There we go. Oh, all right, I think I covered it. So hope this helps y'all. And if it doesn't, well, you know where to find me and how to email me. So have a great week. Bye.